Cool. Go for it.
Perfect. So today we'll be discussing Tree of Thoughts, which has been a very highly requested paper, and for good reason. It's quite fascinating. I think it's a significant improvement in the state of the art for specifically LM's ability to solve complex multi-step problems, particularly open-ended ones where the correct or optimal answer is not completely deterministic, like with math, for example, is the right answer is much more clear, but like the true potential of Tree of Thoughts in a generic way is more about answering open-ended questions like writing or answering complex user queries where the correct answer isn't as clear. So LMs traditionally, like GPT from OpenAI, Palm from Google, have shown an increasingly impressive ability to complete a lot of different tasks in zero shot or few shot settings. Tasks that require symbolic, common sense, knowledgeable reasoning. The paper says mathematical. I would take issue with that. They're pretty bad at math, but it's pretty surprising given how capable LLMs today are that their underlying mechanism for all of the progress is still just original autoregressive token generation, uh, which makes token level decisions one by one in a left to right fashion in English. Uh, and it's a fairly basic and uh, at this point quite quote unquote old uh, technique. And even so, we've been able to see pretty amazing leaps in LM performance over the last few years. So the authors of the paper ask, is such a simple mechanism sufficient for an LLM being built as a general problem solver, uh, not just the kind of chatbots that a lot of LMs up to this point really excel at? The motivation of this paper is to be able to truly build a more capable reasoning agent that's able to self-reflect and make and alter its choices based on the self-reflection, which we'll get to in a little bit. So we'll look at figure 1 here first. So all the way on the left, figure 1A is input-output prompting. This is just like if you're using GPT-3 and you just give it an input and then get its output. Chain of thought prompting, which a few months ago was the state of the art for eliciting more coherent and oftentimes more likely to be correct answers than simple input output prompting. And then really chain of thought prompting essentially just boils down to telling the LLM with every prompt, reason step by step, be explicit about what your like intermediate thoughts are, write them down, and iterate over them. Self-consistency with chain of thought is the LM does the same chain of thought a bunch of times, but with it does it several times, and then based on the end outputs of every branch of their chain of thought, they then choose the answer that has the most quote-unquote votes, or is the most consistent across all possible or all end results of each chain. So it's just like voting, which enables the LLM to better weed out chain of thought answers that are likely to be incorrect or kind of an extraneous outcome. So then true thought, you can see it a bit in figure 1D, but it takes self-consistency chain of thought, and it's like if you mixed all of the different chains together. So instead of evaluating only at the end, like with self-consistency chain of thought, where the evaluation is only at the final stage where there's the voting, Tree of Thoughts is able to make evaluations and reflections and choices about where to continue at every stage of the chain of thought, which is really the new differentiating factor over the current state of the art, which is self-consistent with chain of thought for most applications. So they talk about these two different ideas throughout the paper. I think it's worth going over right now just so we know the terminology. So research on dual process models from human psychology suggests that most people have two modes of thought where they engage in decision making: fast, automatic, unconscious mode, which they refer to as System 1, and a slow, deliberate, conscious mode of reasoning and decision making called System 2. These two modes have previously been connected to a variety of mathematical models, like machine learning models. For example, in reinforcement learning within humans as well as other animals, researchers have explored circumstances under which humans and animals engage in associative, quote-unquote, model-free or deliberative model-based planning. These simple associative choices, when applied to large language models, are also reminiscent of System 1, so the basic input-output model that we saw in Figure 1a, that simple autoaggressive token generation within LLMs, you can think of as reminiscent of System 1 within human decision making. And therefore, because that's the current paradigm with token generation with large language models, the authors of this paper theorize that therefore LLMs may benefit from augmentation to try and produce within the LLM a more systematic and deliberate, quote-unquote, System 2 planning process that has the benefits of over System 1, including that a System 2 planning process would maintain and explore diverse alternatives for current choices instead of just picking one. And then also, at every step, the LLM would evaluate its current status and actively look ahead or backtrack in order to make more global decisions. So it's able to take into account more than just its immediate current state, and is able to navigate and move up and down the search tree progressively. So now with a little background about AI and planning processes, like search is probably the most fundamental topic within artificial intelligence over the last like 6 decades or more at this point. So drawing an inspiration from planning processes and search processes from the 1950s. Research at that time and AI research at the time categorized problem solving as a search problem through a combinatorial problem space, which they represented as a tree. So that's the inspiration or the conceptual foundation that the authors of this paper used to propose tree of thoughts, which is what this paper is about. And it's a framework for general problem solving with language models, as we saw in Figure 1 above, which is this figure. Existing models sample continuous language sequences for problem solving, while in contrast, Tree of Thoughts actively maintains a tree of thoughts where each thought is a coherent language sequence that serves as an intermediate step towards problem solving. Such a high-level semantic unit of where each thought is a sequence instead of each iterative semantic unit the model is working on. So in Tree of Thoughts it's the semantic unit is a sentence, where in traditional autoaggressive generation, the semantic unit is just a token. So with such a high-level semantic unit, it allows the LLM to self-evaluate their progress through intermediate thoughts that they make towards solving the overall high-level problem. And they are able to do this through a deliberative reasoning process that's also instantiated through through language. This implementation of search heuristics, which is how it does the self-evaluation process at intermediate thought stages. That search heuristic comes via in Tree of Thoughts. It comes via the large language model's self-evaluation and deliberation, and that's a new novel addition to the literature in this paper over past research. So they combine this language-based capability to generate and evaluate diverse thoughts with search algorithms. Um, in this paper, they specifically talk about breadth-first search and depth-first search, which allow for systematic exploration of the tree of thoughts with both looking ahead and backtracking when they use both BFS and DFS. Breadth first search and depth first search are probably the most fundamental and like basic search algorithms within artificial intelligence. They're explained later on, but if you are interested and would like to learn more about search or even just have a great foundation for AI in general in the field as a whole, Berkeley has a great AI course, which is CS 188. It's available online. All the lectures and slides are great. And also, what I really enjoyed when I did the coursework many years ago was uh, all of the coursework is implementing search algorithms with Pac-Man. So it's a very fun and engaging course system that they've designed to teach AI fundamentals. So just a resource if anyone wants to learn more about search specifically. That's where a lot of the course, especially in the beginning, focuses on. So with Tree of Thoughts, they use GPT-4. They mentioned the temperature later on, which we'll get to. But they choose 3 different evaluation data sets. So Game of 24, which is an additional math game, or not an addition only, but a math game, creative writing, and then a crossword game. The crosswords are 5 by 5. So these tasks, why they chose them is they require deductive, mathematical, common sense, lexical reasoning abilities, as well as a way to incorporate systemic planning or search of the Tree of Thoughts. So they show that Tree of Thoughts obtains superior results on all of these tasks when compared to the current state of the art, which is chain of thought with what is it? Chain of thought with self-consistency. And that's because Tree of Thoughts is able to show a greater degree of generalization and flexibility over the current state of the art. Also, Tree of Thoughts is a new and unique way to generate as well as evaluate thoughts, as well as backtrack and move throughout the search tree. So it's those unique aspects of Tree of Thoughts that enabled Tree of Thoughts to outperform the current state of the art in these specific evaluations. Also, later on, they see how different components of the Tree of Thoughts architecture affects the overall performance by doing systematic ablations. And an ablation is just where they remove one component to see how worse the architecture performs without that one component. And when they compare that architecture without that one component versus the architecture that's complete, they're able to see what the delta is, and that delta is therefore they're able to know that that delta was caused by the removal or ablation of that one specific part of the architecture. So background, which we already went over, input output, which is just really basic autoregressive generation, chain of thought prompting, self-consistency. So chain of thought with self-consistency improves upon chain of thought because they're generally different thought processes for the same problem. For example, different ways to prove the same theorem, and the output decision will be more faithful with self-consistency with chain of thought because it explores a richer set of all possible outcomes and thoughts, and then has a voting system at the end to decide which to choose. However, within each chain, there's no logical or local exploration or backtracking of different thought steps, and the most frequent heuristic at the end stage of each chain of thought only applies, and therefore the output space is limited. Or sorry, the voting metric or heuristic at the end voting stage only applies when the output space of possible outcomes of each chain of thought is limited. For example, a multi-choice question and answer. So a quote from a 1950s computer scientist, artificial intelligence researcher that is timely or pertinent is, "A genuine problem-solving process involves the repeated use of available information to initiate exploration, which discloses in turn more information until a way to attain this solution is finally discovered." So research on human problem solving suggests that people search through combinatorial problem space, a tree where nodes represent partial solutions and intermediate steps along a solution track, and the branches correspond to operators and that modify the individual partial solutions of the nodes. So like each branch in between a node represents the operation that goes from one node to the other. So which branch is taken is determined by heuristics that help the LM navigate the problem space and guide the problem solver towards a solution. So this highlights two key shortcomings of existing LM approaches when used to solve general problems. First, locally, current LM solutions don't explore different continuations of a single thought process or branches of a tree. So imagine you're 3 nodes down on a branch uh, with chain of thought, with self-consistency of chain of thought. Uh, at every node, the LM only chooses one child node to explore, but with tree of thoughts, even if you're several nodes deep in a chain, the LM can still explore multiple children of that node, uh, which, for example, is like this, where even, for example, you could have the LM, even though it's 2 levels down right here, explore both of these options and decide on which one. So that's what's unique, and that's what they mean in this when they were referring to exploring different continuations of the same thought process or the branches within a tree. So second, the second limitation of current LM approaches is that globally they don't incorporate any type of planning, look ahead, or backtracking to help evaluate these different solution options. The kind of heuristic guided search that seems characteristic of human problem solving as we understand it and experience it. So to address these shortcomings, they introduced Tree of Thoughts, a paradigm that allows LLMs to explore multiple reasoning paths over thoughts, uh, which we saw in Figure 1. Tree of Thoughts frames any problem as a search over a tree, where each node is a state, representing a partial solution with an input and a sequence of thoughts so far. So a specific instantiation of Tree of Thoughts involves answering 4 questions. So like implemented Tree of Thoughts requires the answering of 4 different questions in order to implement it. So the first is how to decompose the intermediate processes into thought steps. So how do you break down a large overarching goal into the intermediate thought steps that will be the nodes within the chain, as well as how to generate potential thoughts from each state. So how do you generate the next nodes? Uh, Also, you have to answer how to heuristically evaluate states. So how to decide which node of the ones you've explored to continue down, as well as which search algorithm to use. In this paper, they explore DFS and BFS, but there are many other search algorithms that you could choose, and that will be like future research that expands on this. So thought decomposition, the first part of implementing tree of thoughts is well, chain of thought samples coherently without, or chain of thought samples thoughts coherently without explicit decomposition, uh, which just means chain of thoughts, it's only about the outcome. The individual intermediate steps and thoughts are not explicitly decomposed as the solution. In contrast, Tree of Thoughts leverages problem properties to design and decompose intermediate thought steps. So, in general, a thought should be small enough so the LM can generate promising and diverse samples. For example, generating a whole book would be too big to be coherent and to produce meaningful and useful node or children nodes from your current node. Uh, Yet the thought has to be big enough so the LMs can evaluate its prospect towards problem solving. For example, generating one token at a time and having that be the smallest semantic unit would likely be too small for the LM to be able to effectively evaluate whether or not that next predicted semantic sequence is likely to actually further the LM's journey towards solving the overall problem. So now with thought generators, there are 2 different thought generation mechanisms they propose for the implementation of tree of thoughts. So the first is sampling. So uh, this, there's a, where is it? I think this is the example they refer to. So here are just the 2 different ways that they generate the next possible uh, step or child node. So they either propose or they try different possible values and then use a value heuristic to evaluate them. So they either sample possible outcomes or they ask the LM using a propose prompt, which is essentially just saying propose what the next step would be. So this works better when the search space is more constrained. For example, each thought is just a word or one line of text. So proposing different thoughts in the same context avoids duplication, which would be a problem if you applied sampling to a search space where the search space is more constrained. You would likely get and have the LM needlessly evaluating duplicate samples. So then the state evaluator, given a frontier of different states, so possible future states, the state evaluator evaluates the progress that each future possible state makes towards solving the overall problem. So therefore, it serves as a heuristic for the search algorithm to determine which states to keep exploring and in which order. So the state evaluator is what is driving and giving the LM indications about which states it should explore further. So traditionally, with very old AI like Deep Blue, which was the IBM program and computer that beat Gary Kasparov at chess in the 90s, as well as AlphaGo, which was Google's Go playing AI that beat the best human player a few years ago. So those heuristics were essentially programmed because their search domain and problem domain were so specific. In contrast, because Tree of Thoughts is designed to be generalizable, they propose a third alternative, which is using the LLM itself to deliberately reason about states. So when applicable, a deliberate heuristic can be more flexible than a programmed one, and be more sample efficient than learned models. So they're essentially using the LM to give or to be a heuristic for the LM's own search of the Tree of Thoughts. So there are two different options they propose for that, or what is the state evaluator. So similar to the thought generator, they consider two options to evaluate states, either independently or together. So the first one is a value state evaluator, where they value each state independently. So the value of with the LLM and the current state as the domain, they then evaluate the likelihood that the next state on the horizon would further the LLM's overall progress towards the goal. So a value prompt state evaluator reasons about the state S, which is the an element of the horizon, to generate a scalar value, V, so for example 1 to 10, or a classification, like sure, likely, impossible, that could then be turned into a heuristic value for the LM to be able to evaluate each state in the horizon. So such evaluations don't need to be perfect, they just need to be approximate, that's why it's a heuristic. So the other option for a state evaluator they propose is to vote across states. So when a problem success is harder to evaluate directly, for example, whether or not a passage is coherent or not, it's natural and it's a better fit to instead compare different partial solutions and vote for the most promising one, because it's difficult without comparing against the other options to evaluate whether a specific paragraph of text, for example, is good or not. It's really all about whether its performance relative to the other options. So that's in scenarios like that, a voting state evaluator would be optimal. So this is similar to a stepwise self-consistency strategy, which means for they're able to cast or which state to explore as a multi-choice question, and the LM then uses samples to vote on it. So for both strategies, they could prompt the LM multiple times to then aggregate the value or vote results to trade time resources for more robust heuristics. So essentially what they're just saying here is, like how self-consistency with chain of thoughts makes a bunch of chains and then evaluates all the end inputs, they're essentially saying it would be possible to do self-consistency with tree of thoughts, where they would run multiple trees and then aggregate the results at the end to possibly get better results, more faithful results, or more robust heuristics. So the fourth and final component of Tree of Thoughts is the search algorithm. So within the Tree of Thoughts framework, you can plug in and play with different search algorithms depending on the tree structure and what your problem domain is. So they explore two of the most simple search algorithms. and they leave more advanced ones. Like A-star is probably the most prominent, more advanced search algorithm that has its own built-in heuristic. So the two search algorithms they explore are breadth-first search, which BFS maintains a set of the most promising states at every step, and then it evaluates. So if it's like, let's say 3 nodes deep, it's evaluating all of the possible children nodes from the current node and is looking at all of them one layer at a time. In contrast, depth first search uh, goes all the way down one branch of the tree to find the end result, and then whether or not that's a solution or not, it then traverses back up the tree and continues down. I don't have a diagram here, but if you look it up online, the visualizations of BFS and DFS make it a lot clearer what this means in practice. But BFS is essentially like a shallow search, level by level, where DFS drills all the way down along the first path that the AI gets on, and it drills all the way down until the final leaf node of that branch in order to evaluate whether or not it's a success or not. And then if it's not, it goes all the way back up and restarts this process. So conceptually, Tree of Thoughts has several benefits as a method for general problem solving with LLMs. The first is that generality. So in contrast, input output, chain of thought, and chain of thought with self-consistency, as well as self-refinement, can be seen as special cases of tree of thoughts, which just means that all of those prior works are variants of tree of thoughts where the trees are limited in breadth and depth. So another benefit of tree of thoughts is that it's modular. So the base LLM, as well as all of the options that the creators choose for thought decomposition, generation, evaluation, and your search algorithm can all be varied independently. So it's a modular system where you can mix and match components for the specific domain you're applying Tree of Thoughts to. So the third is that Tree of Thoughts is very adaptable. It's able to be applied to a lot of different problem properties and domains. It's able to be used with LLMs that have varying capabilities, and resource constraints can be accommodated within the Tree of Thoughts model. As you can give the LLM theoretically a budget, and it can make choices about exploration based on that budget. So convenience, no extra training is needed, just a pre-trained LLM sufficient. There's no fine-tuning needed. Although they talk about later on that future work could involve a fine-trained LLM specifically for a Tree of Thoughts use case. So experiments, we will go over this pretty quickly. It's not super interesting other than just knowing the high-level results. So deliberate trees in Tree of Thoughts produces better results. So deliberate search compared to chain of thoughts or chain of thoughts with self-consistency, which don't have deliberate search. Tree of Thoughts, which has deliberate search, produces superior results to the current state of the art. And more importantly, Tree of Thoughts has proven itself through these experiments that it's an interesting and promising new way to use language models to solve problems that require search or planning. So game of 24, the inputs are 4 numbers, and the question is, given these inputs, whether a solution could be made to equal 24. So here's an example. So figure 2, at each node, in order to generate the next node, there are 2 different ways that they talked about, either proposing, which is essentially just telling the LM propose what the next step could be, or trying possible values as a solution and then valuing them and seeing whether they get closer or not to the overall end goal. So baseline, when they were comparing input-output, they used 5 in-context examples. For chain of thought prompting, they augmented each input-output pair with 3 intermediate questions. So the context examples or the shots they gave to the chain of thought prompting model for chain of 24, the few shots they gave to the chain of thought model had the intermediate steps that the chain of thought model would need. So they augmented the input data for chain of thought specifically. And then for each game, they sampled both input output as well as chain of thoughts, prompting 100 times. They considered chain of thoughts with self-consistency as a baseline, which takes the majority of the output of the 100 chain of thought samples and then uses an iterative refine approach on the top of the IO samples for at most 10 iterations. So essentially just doing chain of thoughts several times and then choosing the best outcome based on a voting structure at the end. So with game 24 specifically, they have a ground feedback signal about equation correctness, which is essentially just saying external to the LM, there's an indication it has about whether a mathematical statement is true or not. So it has access essentially to like a calculator you can think of. Like it's not doing the math on its own. It's being told about whether or not mathematical statements are true from an external source. So for tree of thoughts in game of 24, to frame game of 24 into a tree of thoughts, it's natural to decompose the thought into 3 steps, each with an intermediate equation. So like shown in step 3, like here are the different intermediate equations of taking these input values and getting to 24. So they perform BFS in tree of thoughts with the game of 24 setup. At each step, they consider the 5 best candidates to perform breadth first search in tree of thoughts. They prompt the LM to evaluate each thought candidate as a sure, maybe, or impossible rating with regard to whether that next child node is sure, maybe, or impossible to achieve 24. So the aim is to promote correct partial solutions that can then be predicted within a few look-ahead trials, so exploring down the tree. And by rating possible future nodes as sure, maybe, or impossible, they're also able to eliminate impossible partial solutions based on just the too big or too small common sense reasoning that the LM is inherently able to produce. So in the results, Tree of Thoughts with a breadth of 1 already achieved a success rate of 45%, while when they had a evaluation metric of 5 different nodes for every intermediate thought, Tree of Thoughts was able to succeed 74% of the time. And for comparison, like the prior state of the art was Chain of Thoughts with self-consistency, and it's able to only achieve 9%. So even just with exploring a single child node at every intermediate step, the Tree of Thoughts was able to overachieve the current state of the art by 5 times, and with a larger search space or the ability to search more, Tree of Thoughts was able to succeed 3/4 of the time. So with creative writing, they which is the next evaluation set they use for Tree of Thoughts, they create a creative writing task where the input is 4 random sentences, and the output should be a coherent passage with 4 paragraphs that each end in the 4 input sequences respectively. So such a task is open-ended and very exploratory, and challenges creative thinking as well as high-level planning are involved. So unlike the prior Chain of 24, there's no inherent ground truth about whether or not a state is correct or not. So there's no ground truth about whether a possible future generation is good or not. They focus on evaluating the passage coherency instead in 2 different ways. So they use GPT-4 with a zero-shot prompt to provide a rating or a scalar value of 1 to 10. As well, they also do this with human judges who compare outputs between the different methods and choose the optimal one. So with Chain of Thoughts, when with creative writing, they prompt the LM to make a brief plan, then write the passage. So in this case, with Chain of Thought, the plan serves as the intermediate thought steps. So they consider an iterative refine method on top of a random input-output sample for each task with Chain of Thoughts, where the LM is conditioned on input constraints, and the last generated passage to decide if the passage is already perfectly coherent, and if not, it'll generate a refined one. So that's essentially just evaluating whether or not the current state is the leaf terminating node, or whether or not the LM should continue iterating and trying to make the passage more coherent. So with tree of thoughts, with this evaluation set, the LM generates 5 plans at each intermediate node and then votes on the best one. Similarly, it then generates 5 passages based on the best plan and then votes for the best passage to then go to the next step. So the results, figure 5b, which is right here, shows that humans consistently prefer tree of thoughts over chain of thoughts or other results. They're similar about 38% of the time, but 41% of the time, human evaluators prefer tree of thoughts over chain of thoughts. So lastly, iterative refining. The iterative refine model is a more effective way to accomplish natural language tasks like this. And that using that iterative refinement model improves input-output coherency from 6.19 to 7.67%, and tree of thought coherencies improve from 7.56 to 7.91. So they believe that it could be thought of as a third approach to a thought generation in the tree of thought framework. That is the iterative refine model. So they think that could possibly be a third of thought generation approach within tree of thought, where new thoughts can arise from refining old ones instead of generating completely new thoughts. So finally, in Many Crosswords, so in Game 24 in creative writing, tree of thoughts, the tree of thoughts itself, like the search tree, is relatively shallow. It has like at most 3 steps are needed to reach the final output, so the search space is not that large. In contrast, they explore in this evaluation 5x5 mini crossword puzzles, which have a much larger and harder search problem, or they have a much larger search space, which means it's a harder search problem because it involves natural language and the combinatorics of that. Even with a dictionary, still leads to a many orders of magnitude larger search space in this task compared to the prior ones. So they aim to explore the limit of LMs as a general problem solver by exploring its own thoughts and guides and having the LM guide its own exploration and deliberate reasoning through heuristics, which is tree of thoughts generally, and they apply it to many crosswords. So the task setup, they get a bunch of games from an online source. They notice that adjacent games within this dataset sometimes contain similar clues. So therefore, they space out for both the training or the example prompts and the testing. They space out and choose at random intervals from this dataset. So therefore, it's less likely that there will be any related clues within the different puzzles they're giving for evaluation. So tree of thoughts with the mini crossword, they leverage a depth-first search, DFS, that keeps exploring the most promising subsequent word clue until the state is no longer promising. So therefore, it drills all the way down, sees whether or not it's still promising, and if not, it backtracks up to the immediate parent node and explores alternate thoughts. So it goes down a different sub-branch. So to make the search space more tractable, subsequent thoughts are constrained as to not be able to change any filled words or letters. So the tree of thought has at most 10 intermediate steps. And what they mean by this, when they say subsequent thoughts are constrained not to change any filled words or letters, it means that once an LM puts a letter or word into its crossword as it's solving it, it can't explore a state where it then deletes or rewrites or changes that letter later on, because they need to do that in order to prune and make the search space more tractable. If they didn't do that, as they show later on, the LM struggles and also just the search space is unreasonably large. So for thought generation at each state, they translate all the existing thoughts, which are, for example, at the horizontal row, number 2, the word is motor, or at horizontal row or horizontal column number 1, the word is tasks. So those are the intermediate thoughts, which are the possible states, and the letter constraints as well for the remaining clues. So based on the current thoughts, which are the current words that have already been filled in, the tree of thoughts within the system then generates all the constraints for the remaining clues and provides that also as the current state. So then the prompt is a proposal prompt, which asks the LM to propose 5 different candidates for where and what to fill in as the next word, such that it fits in within the current words as well as all the constraints that are as a result of the current thoughts. So how a state is evaluated within Many Crosswords, this is figure 6 right here. So in B, how each state is evaluated is based on the probability of filling in each remaining word clue, and the state is pruned if any remaining word clue is deemed not to be possible to fill in by the LM. So they prune possible future horizon states that couldn't fit inside the crossword, essentially. So for state evaluations, they translate each state into letter constraints for the remaining clues, like they mentioned before, and then they evaluate for each clue to see if it's possible to use that possible clue to fill in inside the crossword given the current constraints. So if any proposed or remaining clues are deemed impossible, then the exploration of the subtree is pruned, and DFS backtracks to the parent node to explore the next promising thought. So they limit DFS search steps to 100 and simply render the deepest explored state. So the first explored state that has a correct answer, and that's the final output. So with input, output, and chain of thought prompting methods, they both perform poorly with a word level success rate of less than 16%, while in contrast, tree of thoughts significantly improves all metrics, achieving a word level success rate of 60% and solving 4 out of 20 games. Such a improvement is not surprising, given that input, output, and chain of thoughts, they lack the mechanisms to try different clues to make changes and make decisions or backtrack up the tree, because both IO and chain of thought are essentially a one-way street for the LM as it's filling out the crossword. As it makes a mistake, it can't backtrack up the tree and realize it made a mistake. So now getting on to ablation, and oracles. So when outputting the best DFS state within the crossword, when using an oracle, so an external heuristic that determines the best possible state, when they give an oracle to Tree of Thoughts, it performs much better and actually solves 7 out of 20 games compared to 4 out of 20 games when it doesn't have this oracle heuristic, indicating that their simple output heuristic they used in this implementation could be significantly improved upon, because the delta between the current heuristic and the ideal heuristic, which is the oracle, is 3 more games won. So interestingly, sometimes when the crossword is actually solved, the state evaluator might still deem some words as impossible and prune them. This is likely because 5x5 crosswords by design have some rare or obsolete or arcane words that GPT-4 doesn't recognize and therefore doesn't think are valid words. So given the state evaluation as a pruning heuristic is imperfect, they also explore ablating the pruning, so removing the pruning, and then comparing, and they find the performance gets worse if they ablate the pruning process. So therefore, the pruning does provide some valuable benefit to the Tree of Thoughts implementation. However, it could actually find the correct solution for 4 out of 20 games with the pruning ablated. So although only one of those 4 games was output via heuristic, 3 of those 4 games are games where Tree of Thoughts with pruning cannot actually solve within 100 steps. So there are some crosswords within this data set that the Tree of Thoughts model or architecture is able to solve without pruning, that it cannot solve if it has pruning enabled. So that's an interesting observation and ablation to show that pruning as well as the heuristic sometimes limit the LM's ability to find correct goal states. So what it says is that the pruner that's currently implemented for this evaluation is overly aggressively pruning states. So lastly, they confirm the importance of backtracking by running an ablation. removes the filling, they confirm the importance of backtracking by running an ablation that keeps filling the most promising clue for at most 20 steps, therefore allowing overwrites. So this greedy BFS, which just tries to maximize and always choose the most promising clue. BFS, uh, with this greedy BFS search with a breadth limit of only 1, this performs poorly with a word level success of only 20%. So when they allow the LM to overwrite, it seems the search space becomes way too large and BFS is not able to actually successfully find success states oftentimes. So related work, planning, decision making are both classical forms of AI and AI study that have been around for a long time, and they influence this Tree of Thoughts paper. So smart planning, decision making are critical to achieving predefined goals, as they are trained on vast amounts or LLMs are trained on vast amounts of world knowledge and human examples. They already are known to have absorbed rich common sense about the world that makes it possible for them to propose reasonable plans conditioned on problem setting and environmental states. So the proposed tree of thought architecture approach extends existing planning formulations by considering multiple potentially feasible plans at each intermediate node and then simultaneously looking at them all at each problem solving step and then only proceeding with the most promising ones. So the integration between thought sampling and value feedback organically integrates together in Tree of Thoughts to enable planning and decision-making mechanisms, therefore allowing the Tree of Thought architecture to be more effectively search within the solution tree. So on the other hand, traditional decision-making procedures usually require training with a dedicated reward function and policy models such as reinforcement learning. So more traditional decision-making procedures typically require more domain specification and a domain-specific reward function. So whereas in Tree of Thoughts, they use the LLM itself to provide a value estimation for decision-making and to drive the heuristic. So I use the footnote 2 at the bottom as an example of words, or as an example of possible words within a mini crossword that are correct, but GPT-4 doesn't think are actual words, is agend, which is an obsolete form of agendum, but GPT-4 deems it a typo of agenda. So they note that external retrieval or web interaction, or possibly even just a dictionary being available to the LM could augment the LM's ability for problem solving and also improve its knowledge uncertainty. So self-reflection, using LLMs to assess the viability of their own predictions is becoming an increasingly important procedure for problem solving. So prior work in the literature introduced self-reflection, which is when an LLM provides feedback on their own generation candidates. Other prior work improved on LLM's code generation abilities by injecting feedback messages generated by the LLM itself based on its own code execution results, so that's self-criticism. Similarly, other works introduced a critic or review steps over action states, deciding the next action to take in solving computer operation tasks. Another recent work very relevant to Tree of Thoughts is a self-evaluation guided decoding. So similar to Tree of Thoughts, self-evaluation decoding also follows a tree search procedure, which leaves sampled from stochastic beam search decoding, which are then evaluated by the large language model itself with carefully prepared self-evaluation prompts. So this approach in prior literature used a PAL formulation, which represents thoughts as codes, which makes it more difficult to tackle challenging tasks like creative writing, which they consider in this paper. So Tree of Thoughts, the Tree of Thoughts formulation is thus more versatile and handles challenging tasks on which GPT-4 only achieves very low accuracy with standard prompts. And Tree of Thoughts is more generalizable than prior works that use PAL formulation because the intermediate thoughts in Tree of Thoughts are themselves natural language. So program-guided LM generation. So the Tree of Thoughts paper is related to recent advancements that organize an LM's behavior with symbolic program guidance. We read a paper that was a later development within symbolic program guidance with LLMs, which was LM plus P, which we read a week or two ago. And LM plus P delegates the actual planning process to a classical planner, which is an algorithm from traditional artificial intelligence research. So then future work can also expand on so tree of thoughts can be thought of as a modern rendition of classical search methods for problem solving. For example, it can be considered a heuristic search algorithm like A star, which is a search algorithm that has a heuristic. And tree of thoughts is similar to A star because at every search node, the LM is providing a heuristic self-assessment. From this perspective, their method is also related to neurologic A star. S decoding, which neurologic A star is a prior literature work, I think from 2019, which was inspired by A star but introduces look-ahead heuristics that are efficient for LMs to improve the beam search or top K sampling decoding. So this method, however, is constrained by sentence generation tasks, or it's constrained to sentence generation tasks, whereas Tree of Thoughts is designed for complex multi-step problem solving that is guarded by value feedback and is much more generally applicable. So some limitations of Tree of Thoughts currently is that deliberate search such as Tree of Thoughts might not be necessary for existing tasks that GPT-4 already excels at, and it's an initial step, and as an initial step, this work only explores 3 relatively simple tasks that GPT-4 is quite challenged on, and they explore tasks that require better search and planning abilities than current LMs are able to accomplish or achieve on their own. So, however, they begin to deploy, as we begin as a society to deploy LMs for more real-world decision-making applications, more complex tasks could emerge and present opportunities to apply research like Tree of Thoughts. Also, search methods like Tree of Thoughts require more resources versus just using a simple input-output formulation, because Tree of Thoughts requires more resources than similar sampling methods in order to improve task performance. It needs more resources, but the modular flexibility of Tree of Thoughts allows users to customize such performance trade-offs, and there's also more ongoing work about reducing compute costs. And Tree of Thoughts users or implementers are able to choose different components and decide where they want to spend resources within each several components of the Tree of Thought architecture. So lastly, Tree of Thoughts focuses on using an off-the-shelf LLM, on fine-tuning LLMs using a Tree of Thought style high-level counterfactual decision-making framework. For example, deliberating over potential choices for the next paragraph instead of just predicting the next token. So using a fine-tuned LLM on a Tree of Thought structure might present opportunities to enhance the problem-solving capabilities of LLMs beyond what they showed in this paper. So the broader impact of Tree of Thoughts is that it's a framework that empowers LLMs to more autonomously and intelligently make decisions and solve problems. So while current tasks are limited to reasoning and search problems, further applications of Tree of Thoughts could involve interaction with external environments or humans, could potentially bring, applying this to interactions that involve external environments and humans could potentially bring danger. It's potential that Tree of Thoughts could be abused and be used for harmful uses of LMs. I guess this is a kind of quote-unquote required paragraph that every AI author seems to have to put in, which just says our research could be misused. On the other hand, Tree of Thoughts improves the interpretability of model decisions and the opportunity for human alignment, as the resulting representations are readable, high-level language, natural language, reasoning instead of implicit low-level token values. So the fact that the intermediate steps within Tree of Thoughts allows humans to understand the intermediate reasoning steps of the LM, which therefore likely increases humans' ability to correctly align the LM with our values and goals because we understand the internal intermediate thought steps. So as we talked about earlier, System 1 and System 2 methods of decision making. So System 2, which is a more deliberative, slow process, is based on searching a tree of possible paths to a solution for the problem. So, Tree of Thoughts provides a way to translate classical insights about problem solving into actual methods for contemporary LLMs. At the same time, LLMs address a weakness of these classical planning methods by providing a way to solve complex problems that are not easily formalized, such as creative writing. They see the intersection of LLMs with classical AI approaches as an exciting direction for future work. So, prior uh, application of classical AI to LLMs was like LM plus P, and this is another application of classical search to LMs. Any questions, thoughts?
I'd just like to say well done, Sam. That was very good. I can certainly see the power potential in this system, especially as we would be essentially pre-programming and tailoring those branches, and you could, and because excuse me just now, and because we can essentially direct this AI's intelligence currently however we like, and with this system, yeah, you could essentially get theory crafting anything right now. Actually, pros and cons, but again, comes down to the user.
Yeah, for sure.
I have one question. How do you think a system like this would operate parallel with real-time data analysis?
With what data analysis?
Real-time.
Real-time data analysis is, I guess, if the data analysis was a search problem or could be mapped to a search tree, I guess it could be applied. But uh, I guess data analysis isn't as much, or at least oftentimes isn't as much of a search problem with intermediate like steps to a solution. Does that make sense?
Yeah, yeah. Um,
I'm not sure if I totally understand the question you're asking.
okay, let's be a bit more specific then. So say we tailored up the three thoughts to essentially be areas of processing for, let's say, trading indicators. Okay. Now, you could feed that system all the indicators, as many as you like, even averaging them out and combining some, and then having that do its thing, but also it's learning at the same time to, you know, solve. Maybe not necessarily. Well, could arguably be the subjective as a problem because it's having to come to conclusions on the data, which is in itself. Mm, mm, sorry, I'm just thinking. Yeah, well, that would be the idea behind it. Is we'd be running the real-time data to essentially for it to process. I have read though. 2 seconds. Potential challenges. Current units of thought, evaluating these units, defining these units, and evaluation criteria for real-time, given the
Does
dynamic.
anyone else have any questions about the paper?
Oh, sorry.
No problem.
Yeah, I have a sort of a technical question. So they say it's like an A-star algorithm, but isn't A-star a graph algorithm? And then this is a tree algorithm, right? So, why they're saying it's a A-star like algorithm? It's probably way
Uh,
technical, but
yeah, no, I understand what you mean. I'm pretty sure the reason they say it's A star like is that it uses a heuristic to evaluate intermediate nodes um, to inform what search steps are taken next, and in that way, it's similar to A star. So you couldn't directly use A star as a drop-in replacement for DFS or BFS in this example, but conceptually, Tree of Thoughts uses heuristic to explore or to decide which parts of the tree or search space to explore, similar to how A star uses a heuristic to decide which parts of the graph to explore.
Yeah, so speaking of that, so the heuristic, they ask the LLM to produce its heuristic. Like they say, okay, here I'm at this node, give me how good the action is going to be. I I don't think it's going to be reliable. And you say, how good is this state? Give me a score between 0 to 100. And I mean, there's no way to. I mean, how do we know it's reliable, that number?
So we don't, and because a heuristic doesn't need to be perfect, it just needs to kind of give an LLM to point in the right direction, so it just doesn't go exploring completely obviously wrong answers. So um, I think a good example of why a heuristic doesn't need to be perfect but just okay is this game of 24. So of the possible combinations, uh, for example, like one possible combination when you get the four numbers at first would be to add 10 and 13 together. But the LM, through its heuristic, is able to know that's definitely not going to work because one is also not a number. And if you add 10 and 13 together, you get 23. So there's no way that that search or that child node could be on the branch that leads to success. So that heuristic that's able to eliminate just obviously wrong or incorrect child nodes is
But
why the heuristic is able to work. And it doesn't need to be perfect, it just needs to be able to eliminate the clearly wrong answers.
the opposite is also true. So if it scores the right answer as very low, it will never explore that, and then you never get to the right answer because it made a mistake, right?
Yeah, you're right. And like with the uh crossword puzzle, their heuristic is actually does actually prune correct goal states from the search tree, and is
Mhm.
therefore the heuristic being incorrect means the LM is not able to solve problems. So yeah, the heuristic and its quality definitely does impact the overall viability and success of the tree of thoughts architecture for achieving the goal state.
So I had one more question, just more like a comment. So OpenAI has a new plugin where if you ask it a question with GPT-4, it'll produce the Python code, um, and similar to what uh, AutoGPT does, and run it. So task 1 and 3, it can now probably do it by creating an exhaustive search in Python and then coming up with an answer, right? Uh, does-
Yeah, yeah, I guess it could. Although that would just be a traditional input-output model implementing a search algorithm in Python, right?
so my point is, like all these 3 examples, it really doesn't show a. These are not like, I wish there was a more interesting uh, metric or test case. Like 1 and 3 is so trivially solvable by a Python code. I mean, 3 requires a lot of human massaging and like input to, and then it's also not very deep, right? So the number of steps that they do. So yeah,
Yeah,
I don't know if there's any other tasks. That's all.
yeah, I guess like these are toy tasks, but the reason why they chose these specific tasks is because they're not trying to compare it against like what could be achieved if someone wrote a Python script. They're trying to compare it against the current state of the art in large language models. So like there are lots of things that LLMs can't do right now that are like those tasks are the frontier of AI research, even though those tasks could be easily achieved by writing a quick Python script, but we're not really comparing tree of thoughts against the baseline of what can be done in Python. We're comparing against the baseline of what's the current state of the art, like chain of thought or just input output.
Yeah, but as I said, the new plugin actually writes the Python code and executes it and gives you the answer. So then, yeah, it becomes like, okay, well, what exactly are we achieving? But anyway, yeah,
Yeah, I guess
I,
I
I
would
mean,
say like from a practical user perspective, you're right, but like from a research perspective, like ChatGPT plus a plugin isn't really like an actual architecture within the literature. It's just like piecing together components, if that makes sense.
yeah, but yeah, that's all.
Can I ask one more question,
Yeah,
please?
go for it.
So the TOT, the evaluations it uses, is it true it's sure, maybe, or impossible?
So that evaluation or those heuristical choices were only for the game of 24 task.
Okay. Yeah, that
Yeah.
makes sense for the game. Definitely not. I was concerned because I thought for creative writing, impossible. No, you wouldn't have that.
No. For creative writing, the heuristic is they have two heuristics. They either ask the LLM, or sorry, for the intermediate heuristic at the intermediate steps for creative writing, they have the LLM compare the different possible completions against each other, and the LLM then chooses the best one.
Okay. Cheers.
Anyone else?
I have another question.
Go for it.
Question about state evaluator. I saw that there are two types of state evaluator, value and vote, and I don't know. I'm not sure what's the difference between them. As I understand, by valuing the states independently, we could vote them by the scalar value we valued. So why they propose two different methods?
So you can think of voting as essentially valuing but ranking. So by voting, you're not able to have a tie, but with valuation, for example, like every possible future child node could get the same value through the score if they're evaluated independently. But if you're voting across states, you're essentially ranking them all relative to each other. Does that make sense?
So,
Did I
yeah,
answer your question there?
yeah, I understand that.
Okay,
Hey Sam, I have a question.
go for it.
When you read through the paper, I don't know if you had a chance to run their original code when you're trying to tinker at it. Wouldn't
I haven't looked at the GitHub, but sorry.
Yeah,
Continue.
essentially the way to describe their BFS search, if you put it in a breadth of 1, how equivalent is it to a chain of thoughts, right? Because structurally it looks like it's the same, however, they end up with different results. So there's obviously something within the inner mechanics that is different.
Yeah, that's a really good question. I guess I'm not totally sure how, when chain of thoughts, how the LLM is choosing each intermediate step, but I guess, like, on the top of my head, yeah, it sounds like it probably should be a similar or the same result, because with a breadth of 1, you're essentially just creating chains.
Yeah, you're creating a linear chain all the way down, right? And if you end up on the wrong path in a local minimum, you're going to end up failing the task, right? It's the same way chain of thoughts would, right? So, but when they listed their results for a breadth of 1, they posted significantly higher success rates on a breadth of 1 BFS chain of tree of thought search than a chain of thought. And it seemed a bit weird because if they're structurally the same, but your tree of thoughts breadth of 1 approach has a significantly higher success rate, then really exclusive of the tree approach or the tree aspect of it, there is something else which is advantaging the tree of thought algorithm that they're implementing, right? Beyond the tree aspect of it. Whether it's in the prompting or it's in the evaluation or the reasoning, something is different. And I couldn't seem to discern what it was.
Yeah, that's a really good point. I'm not totally sure. I'll try and get back to you on that. I want to know the answer to now.
I want to hop in on behalf of one of the authors, Shenyu, I spoke with earlier today. Since
great.
you guys are talking about the code, the GitHub repo, and he wanted to make it clear that there are 2 tree of thought repos. One was potentially GPT created based on his paper, and then there's the official one. And the official one is often not the top result, as it was created after the fact or after the paper versus immediately when the paper was published?
Yeah, I think the official one has the log data that underlies the paper in the repo itself, right?
Yes,
Would
and
someone be able to link both repositories in the chat?
I believe the official repo is at the end of the abstract in this paper.
Yeah.
Right there.
Great. Nice.
Please, yeah, I'm really glad there's great turnout today. Our next session will be on Monday, same time. I've had a few people contact me about presenting papers. I'm always happy to have new presenters. So if there are any papers that you would like to present, feel free to reach out to me and we can make sure to get them on the schedule.
We could also use the opportunity to bring to the front any papers that are standing out at the moment. Would that make sense, or should we do that asynchronously?
I would say I think the best way to figure out what papers people are really interested in is putting emoji reactions on the ones people propose in the thread for paper suggestions, because I prioritize ones that have a lot of engagement for being put in the poll.
Got it. Good.
Yeah, well, I guess I'll see you all on Monday. Have a good weekend.
Thanks for presenting, Sam.
Thank you.
Yeah, of course.